So, hi everyone. Thank you for making time for us today and for coming to hear about SAR, the Enigma. Let's start by talking about how we can embrace the current SAR revolution or what exactly is happening. First, I just wanted to talk about what brought us here. I've already been introduced, so I don't want to talk too much about where I'm coming from, but I guess it would suffice to say I kind of work in between academia and the industry. And it's been really, really interesting for me to see this evolution. In 1992, as the first Earth observation SAR images were transmitted by the ERS and the JERS satellites, I do not think anybody thought about the variety of applications that we see today. Yet, in 2000, the Shuttle Radar Topography mission of NASA mapped global elevations for the first time at 90 meters. Coming from a data-scarce country myself, from India, and as a hydrologist, I can say that this was revolutionary. Never before did we have global elevations to be able to compute any sort of things. But here we were suddenly with 90-meter elevations for all over the globe, including India, and we could start to look at different disasters, specifically hydrological, hydrometeorological disasters, and how they could evolve in space. Then in 2010, the first satellite constellation in space, Cosmos Skymed 1, enabled for the first time sub-daily imaging. It was now possible to get 12 hourly images of synthetic aperture radar, which was never before heard of. In fact, SAR experts who did their PhDs long before used to consider themselves quite lucky to get one image for their use case. But we really were lucky to be alive in the age of big data for SAR. And when I started my PhD, luckily in 2015, at this time, Copernicus Sentinel-1 was already downlinking really high quality systematic SAR acquisitions, and the SRTM-DEM became open at 30-meter resolution globally, which was again a game changer for several types of applications which cannot really function with 90-meter data sets. And as we look to the future, as the talk from Go already showed us, we are now looking more and more at reducing spatial and temporal resolutions. We can look forward to even hourly imaging from Capella, from Synspective, from ISI in the future as their satellite constellations grow and they continue to move along this journey of more systematic acquisitions. So moving from these highly tasking-based acquisitions that currently the commercial SAR sector offers and moving towards more systematic acquisitions, which can then support better environmental use cases. Talking a bit about revisit versus resolution, if we look here on the left-hand side, so the y-axis has resolutions on it and the x-axis has the revisit time. And we can quickly see that the satellite constellations really provide much higher revisit and resolutions and therefore are really specifically useful for some applications such as coastal zone monitoring, highly dynamic ocean monitoring, traffic, and disaster monitoring, all of which are opportunistic in the sense that when a disaster is occurring, you need an observation during this disaster in order to be able to monitor it. And the likelihood of this will increase as many times as you're able to acquire. And therefore, increasing to this hourly temporal resolution is really useful for these kind of use cases. On the other hand, there are, for instance, the global mapping of elevations. Now we have also the World-DEM and the Copernicus-DEM based off of the Tandem-X and TerraSAR-X missions from the German space agency, DLR. And we can see in this context that, of course, we do not need to acquire images maybe at hourly resolutions because also dealing with this kind of data size is non-trivial. And we then go towards the other end of the revisits. We still need relatively high resolution in order to be able to get relatively high resolution elevation estimates, for instance, but we could deal with slightly longer temporal baselines. So for differential interferometry, soil moisture changes, monitoring of agricultural areas where we want to see, let's say, different phenological phases, all of this is possible with slightly lower revisit times and sometimes even lower resolutions. Another interesting point from this graph is to see that if we look at public satellites, so satellites that are from space agencies and not from new space companies, so RISAT-1A, this is from the Indian Space Research Organization, SAOCOM is from Argentina, I think, and then RadarSat from Canada, etc. All of these are more focused towards providing really high quality, perhaps low revisit, but focused on moderate resolution data sets, which are more or less useful for a variety of use cases, whereas the commercial SAR sector is really focusing more on very high resolution, very frequent imaging, which can feed a different set of applications more focused on the industry. For instance, construction was being brought up quite frequently, and this is a space in which the commercial SAR satellites could flourish. Right, I also saw some questions about surface water mapping with SAR, how to map inundation, etc. And for this, I think it's important to understand how SAR satellites function. It was really nice to see that most of you are already working with SAR data, and therefore perhaps you already know this, but for the others that don't know, I will just briefly cover this. So SAR satellites essentially feel the Earth instead of viewing the Earth. So they distinguish between, let's say, differences in roughness. This is one way in which you could look at stuff in SAR data. This is one way for you to interpret differences or distinguish between different Earth features. And the second way to do it is using the difference in how the area was imaged. So let's stick with this for one moment. The difference between systematic acquisitions and commercial acquisitions is not always clear. So when Sentinel-1B stopped functioning, there were a lot of questions, specifically two sisters of SAR, about the utility of other commercial satellites to plug this gap. But the point is, unless an acquisition is systematic in the sense that it can allow interferometry, so what Go was also mentioning, it's not an easy thing to do. You need to have very strict orbital lines, and you need to always follow them. And this takes time to do, specifically with tasking-based satellites. You're not always imaging the same place on the planet with the exact same geometry, which makes differentiating features slightly challenging and interferometry very, very challenging. But when you can do interferometry, this phase, the matching of phase or how the area was imaged provides a lot of information about what has changed there. So if everything stays the same and your satellite, if everything on the planet remains the same and the satellite geometry remains the same, more or less, we should be able to get a near identical image from the same area on Earth. And this is the feature that can be leveraged to detect changes. One of them being changes in water surfaces or surface water mapping. In this context, typically we use the difference in roughness. If the water is still, it causes the radar beam that is being incident on it to be reflected away from the sensor. And so the sensor doesn't really get any returns from the water surface. And we could characterize a typical flooded image or an image with water surfaces in it, a histogram or the distribution of pixel values to look something like this, where you have a water distribution with very low backscatter or returns to the sensor, and you have the land pixels with typically higher backscatter or return to the sensor. And of course, this is possible to divide using a simple threshold in the ideal world, but of course, water is not always still and not always dark on sensors, and that leads to complications, and why there are a lot of deep learning-based techniques being developed now. But in the best case scenario, you could do it just using a threshold, as you can see in this example SAR image from Capella on the right. Then there is this super important use case of mapping elevations with SAR. We already talked a lot about interferometry. I don't want to talk too much more about it, but I just want to show you visually what that looks like. So if this is your SAR satellite, and if you image the same place with the exact same geometry, and the area you're observing has changed, we can use this shift in the return that is coming to the sensor to calculate how far away from the sensor the ground has moved. So it can provide really sub-centimetric accuracy to map land or elevation changes, which is as far as I know, not even possible with really good photogrammetric stereo satellites in the multispectral range. There are, of course, challenges. For instance, radar satellites are side viewing sensors, and they can typically only detect this type of deformation along the line of sight of the satellite, so where it's looking, let's say. Of course, you have to use multiple images. As I said, you need a time series of images typically, which increases processing time. And these are complex data sets. So for example, cloud processing platforms do not have this capability yet. So Google Earth Engine does not host the kind of imagery or the raw data from SAR, let's say, which enables you to do this kind of processing. And finally, in mountainous regions, radar shadow, layover, a variety of geometric effects from this side-looking sensor characteristic can yield problems. Finally, the biggest problem is that very rapid or very large-scale changes cannot be detected. For instance, for Sentinel-1, it can detect up to 0.5 centimeters of subsidence in a day. So if you have construction creating very large buildings where there were no buildings before from within the baseline of a Sentinel-1 acquisition, this is not something that it could detect easily. Right, as we move towards very high resolution SAR, we can now do everything, or more or less everything with it that we could do with high resolution optical. We can count our planes, we can count our ships, we can count our sheep if you were interested in livestock monitoring. And we can do it all during bad weather and at any time of the day and at night. This is, of course, a big, big advantage. We can map oil spills with SAR. This is, again, leveraging the difference in surface roughness. So the ocean typically has these small waves that causes some reflection back to the SAR sensor. So even though it's a water surface, it's always moving. And therefore, oil surfaces on top of this, which cause slightly lower roughness for the area where the oil is already spilled. This can be detected via a SAR image. And finally, I think some of you were also working on this use case, which is forest monitoring with SAR. This is a bit far away from my own area of expertise, but it is possible to monitor forests, estimate above ground biomass, estimate the height of forests using the variety of techniques that I just pointed out. SAR data can also be useful for mapping wetlands and identifying land cover types that are not always distinguishable using optical data alone. I think Go very eloquently mentioned the idea is to bring solutions to people who want to solve problems with this kind of data. And the idea is not just to use SAR data for the heck of it. And therefore, it makes sense to integrate as many data sources as we have to provide as much information as we can towards the problem that we are trying to solve. And this includes, of course, ocean surfaces, current monitoring, ice mass balance, glacier velocity, what have you. So really, the sky is the limit, and now we can do it through the clouds. Thanks a lot for your attention, and I will be happy to answer any questions.